Alright, here is part 2 of our uniform circular motion problem. The first problem, by the way, the numerical answer is 31 meters per second, and you can see that in the previous video. Part 2 is we want to now incline the ramp at an angle, and we want the angle to be such that this car can go around this ramp without relying on friction. So, acceleration is to the right, that's indicated by the arrow, the red arrow there. And you can imagine this car is coming out, at this particular point on the ramp, is coming out of the page and it's traveling in a circle. So what I'm going to do is I'm going to bring up the free body diagram for this problem. There it is. I did it earlier. Alright. So, let's take a look at it. So first of all, I have a coordinate system, x and y. That dashed black line there is the ramp. So right here, that's the ramp. Here is the angle theta. There's only two forces acting. Since we're not relying on friction, there's only two forces. There's the weight of the car bringing it down, and that's in the negative y direction here. And there's the normal force, which is perpendicular to the surface of the road. So it turns out the angle theta, in the previous picture here, is the same as this angle indicated in that red triangle there. So those are the same angles. I'm going to let you verify that yourself. I'm not going to go through that proof. Okay, so to do part 2, we're going to need to use Newton's second law. So, Newton's second law, let's consider the forces in the y direction. So, in the y direction, okay, we have the normal, the component of the normal force in the y direction, plus the component of the weight in the y direction, and this is equal, from Newton's second law, mass times the acceleration, the component of the acceleration in the y direction. Now this car is staying at the same height as it goes around this ramp, so its position on the y-axis isn't changing. So its y acceleration is actually 0. So we have the y component of the normal force is equal to the negative y component of the weight. And the weight is in the negative y direction, so its y component is going to be negative, and it's just going to be mass times the acceleration due to gravity. And of course, since, right, okay, so I think that's the y component. So what is the x component of the normal force? So, in the x direction, we have the x component of the normal force plus the x component of the weight is equal to mass times the acceleration in the x direction. So here the x component of the acceleration is centripetal acceleration. So that's related to the speed the car is going squared divided by the radius of the curve. Other thing to note in this equation is that the weight doesn't have an x component, it's straight down. So this term here is 0. So we have the normal, the x component of the normal force is equal to mass times the speed squared over the radius. Okay, so where do we go from here? Well, the x component of the normal force is equal to the magnitude of the normal force times sine of the angle theta. Okay. We also know that from our previous equation for the y direction, the y component of the normal force is n times cosine of theta. Okay, So from this equation, we can get that the normal force is equal to negative mg. Actually, you know what? I'm off by a negative sign. This should be positive, so I got a positive here because there's two negatives. There's a negative sign when I brought wy onto the right-hand side, and then the negative sign comes from the negative y component of the weight. Then we divide by cosine of theta. Again, so this is solving for this n right here. Okay, and I'm going to take that n and I'm going to substitute it into this equation over here. So we have mg over cosine theta is equal to I forgot something here. I forgot the sign. So I need to include this sign over here. So we have sine theta, and that's equal to mv squared over r. Note the m's cancel. That's what we want. And the sine over the cosine is just a tan. So we have g tan theta is equal to v squared over r. And just giving us a little bit more room. Solving for theta, I'm going to do this in one step. That's just equal to the inverse tan of v squared over g times r. Okay, so v we found before. V we said was about 31 meters per second. G we know is 9.8 meters per second squared, and our radius was 250 meters. So we can plug all that information in, and we'll find that theta is going to be 21.8 degrees. And I guess, how many sig figs do we need here? Let's go back up. It looks like we need two significant figures. So let's round this to about 22 degrees. And there's our answer.